Welcome back to the Science College Readiness course. So far you have studied interpreting data off of graphs to interpret graphs, interpolate, extrapolate, make sense of the data, look at the trends, try to figure out relationships between objects. Another key way to represent data is through a data table rather than a graph. And typically a data table is created to then make a graph. So it's another visual representation of information to help you make sense of relationships and trends of your data. The first thing to discuss is just the basic makeup of any table. Tables always have columns, which are vertical, the up and down. Just think of columns outside of a building. Columns always run from the ground up to the roof, floor to ceiling. Those are the vertical parts of your table. And then the rows are the horizontal part. So knowing columns versus rows is just key terminology for tables. Typically, tables will have headers at the start of a column or the start of a row. And those columns and headers will tell you the information that you're looking for. And usually what you will then do is look for the data that shows when a certain column and a certain row intersect to find out what happened at that point in time. So it's always important when you're looking at data that's represented in a column or a row to know what the heading is, what the units are, and what's being represented so the data itself makes sense. In almost every lab that you will do in a science class, you will collect data, and then typically you will put that data into some sort of a table, and then from that table you will be asked to analyze the data, make sense of the data, interpret what that information is showing you, potentially create a chart, graph, or diagram from the data in that table. And the ACT, there will be questions that incorporate tables and graphs and reading passages in together. What we're going to look at today are different examples of passages and data from passages from ACTs where you're looking at either tables and comparing one table to another, or tables and graphs where you're comparing those against each other. So we're going to start with the three data tables that you see in front of you here on the screen that relate to one experiment where a physicist was looking at factors that impact the amount of friction acting on an object. In this passage, the words in the passage would describe that table 1 shows where a brick was placed first flat, then on its skinny side, and then on its end. So you had different amounts of area of the brick that would be touching against whatever surface it was we were pulling. Then the same experiment was done with a block of wood, and the block of wood had considerably less mass than the brick did. The areas were the same, the sizes of the brick and the wood were the same, they were placed on the same types of sides, and the friction again was measured when this was pulled. And then finally, the block of wood was again pulled with the same areas. However, this time 1.2 kilograms were added to the wood, so that way the wood's mass was the same as the brick's mass. So we could now compare a variety of different objects. We can compare brick versus wood. We can also compare masses, and we can compare masses of the same substance. So a variety of different ways to look and see what impacts the friction acting on an object. And so then the questions that we're going to consider for this also look at those three variables. What is the purpose of table 2 versus table 1? How do table 2 and 3 compare to each other? Why are we using brick versus wood? What's the purpose of making the brick 1.8 and the wood 1.8 kilograms? So a variety of different things to consider. And before we can get into that, let's just take a look at some of the data that's represented here and look at within a certain table, is there a trend that we can notice? At this time, take a look just at table 1, and we're going to pause the video here for a little bit of time. We'll keep the video running, but I will just not talk. And I want you to take a look at the data and see, for the brick, is there any relationship between the surface area and the friction on the brick? Hopefully what you've seen is that 7.1 and then 7.3 and then 7.2 are all pretty darn close to each other in terms of the size of the friction, and that there is no clear trend of an increasing or decreasing amount of friction as we're going. So the area of the brick doesn't seem to really have much of an impact. take a look at the two woods as well, the wood 0.6 and the wood 1.8 kilograms. As we take a look at that data, again, is there a clear trend? Does the data clearly go up or down as you change from one surface area to another? It appears that the 1.8 does go from 3.5 to 3.6 to 3.7, so it is increasing in the same general area, but not changing a whole lot. The wood 0.6, that data is going up and down, so there is no clear trend there. So one thing to consider from this data is that it appears that the surface area really has no impact on the amount of friction that is acting on an object. So the next thing to consider would be, how does mass impact? So now, if I'm only looking at mass, I want to look at the substance itself. That being only one variable is the mass difference between the two. The brick has 1.8 kilograms and the wood has 0.6 kilograms. But then I'm not only looking at two different masses, I'm also looking at two different materials. So we have two variables in here, and we cannot tell which would impact the experiment of those two. So we want to have only one variable, so we're going to keep the wood the same and take a look at the differences in the mass. So now, as I look at the amount of friction acting on the 0.6 to the 1.8 kilogram, take a look there, and as we look at 180 cubic or squared centimeters and 180 square centimeters, if I look at those two pieces of information, and then I look again and again, as the areas change, the friction definitely is higher for the 1.8 kilogram block of wood than for the 0.6 kilogram block of wood. And in each case, it appears to be about triple the amount of friction as the mass has tripled. The final area that we can consider here is looking at, when the masses are the same, does the material have an impact on the amount of friction? Well, 1.8 kilograms and 1.8 kilograms. So those two have the same mass. So now we're not going to consider this table in the experiment, because now we have, again, two variables, different material and different mass. So now we have same masses, but we have different materials, brick and wood. And so the questions here, again, would be, does the material impact the amount of friction? Well, for the same mass and the same surface area, it appears that the friction is about double for the brick everywhere that you're looking than the wood. So again, it would be a clear connection and clear correlation from the data that the material does impact the amount of friction. So questions that would be asked would be like what we've talked about in terms of, how does increasing the amount of mass impact the amount of friction? So now you're looking just at the masses. We could ask you, how does changing the material look? Well, in that case, you need to make sure that the only thing different is the material, wood versus brick. Other questions that we talked about again are, for a brick, does the surface area impact the amount of friction? In this case, you could say no. So a question that would be asked would be something like, if that same brick were put onto tiny little pins, so the amount of surface area that was in contact to be pulled were significantly reduced, what would you anticipate the friction to be in choices of 1.8, 3.5, 7.2, and 10.5? Well, what we've seen is that the surface area doesn't impact the amount of friction, so we would anticipate that the amount of friction would be pretty close to 7.2, not having an impact. Another question could be, for a block of wood, if a second block of wood were stacked on top of the one from table 2, so that the mass became 1.2 kilograms, what would we expect to happen to the friction? Well, we saw from table 2 to table 3 that as the mass tripled, the friction tripled. So we would expect that if the mass doubled, the friction would double. So we would expect to see around 2.3 to 2.4 newtons of friction if the mass were doubled. So a lot of different information that we can pull just by looking at the numbers and comparing the headings to make sure that we're comparing masses when we're supposed to be comparing masses, or materials when we're comparing materials, and looking for trends within the data table. Here's another example of a data table, and there's another slide after this that will show you a different table with similar data in it that's comparing a different impact with the peony seeds. So for this one, we have these seeds that we're looking at how many of them are going to germinate. And the table, the wording above the table tells us that these different seeds were stored at 5 degrees Celsius for a certain amount of period of time. So that's what's in this first column over here. This is how long they were stored at that temperature, and then were placed into damp petri dishes at a variety of different temperatures, and were looked to see after a certain amount of time how many of them germinated. So what we're looking at here is how many seeds germinated. Each one had 20 seeds in them, 25 seeds in them, and we're looking to see how many of those 25 seeds germinated. So some clear things that we can look at here. The ones that were stored for 0 weeks, none of them germinated. The ones that were stored for 10 weeks, as I go down each of the columns, the ones that were stored for 10 weeks at 5 degrees Celsius all germinated more. So that would tell me that if we can store the seeds at a certain temperature for a certain amount of time, we'll probably have a better germination rate. Other things to consider then are looking across for at the same amount of storage, let's say for 8 weeks. If I look at the different temperatures now that they were allowed to germinate at, 13 degrees, I had 7. At 18 degrees, I had 22. At 23 degrees, I had 18. And at 28 degrees, I had 0. Going down to 10 weeks, then I had 15, 24, 21, and 1. So a clear question could be, at what temperature is ideal for germination? Well, more seeds germinated at the 18 degree Celsius than any other. So we would want to have the petri dishes that are germinating the seeds at 18 degrees Celsius to have the highest rate of germination. Another question could be, at which temperature should we not store the peony seeds in order to have them germinate? Well, if you look at 28 degrees Celsius, only one seed ever did germinate. The rest of them all died. So none of these are growing. We definitely wouldn't want to have 28 degrees Celsius. Another question, of course, would be, is there an optimal amount of weeks to store the seeds at 5 degrees Celsius? Well, the one that grows the most seeds would be the best. So storing them for 10 weeks is the ideal amount of time based off of this experiment to store them before putting them at a different temperature to germinate to allow them to have the highest amount of germination. So this would be one experiment. We're going to look at some data. So now this was the follow-up experiment. And what was described for this experiment is that since in table 1 we saw that 10 weeks of storage was the maximum time, or when we got the most amount of seeds to germinate, now let's see if at that 10 weeks does the storage temperature before we allow them to start germinating matter. So all of these seeds were stored for 10 weeks, but some were stored at 0 degrees Celsius, 5, 10, 15, and 20 degrees Celsius. They were then put into petri dishes with damp paper towels and maintained at 13, 18, 23, and 28 degrees Celsius for a period of 30 days. So at the end of 30 days, at 18 degrees Celsius, we had 24 of the 25 germinated at 0 degrees when they were stored there, 23 germinated when they were stored at 5 degrees, and then it dropped way down. So again, the trends show you that when you jump up to the 10 degrees Celsius storage range or above, you're not going to get a whole lot of germination. So we want to make sure that we're maintaining at 0 or 5 degrees Celsius. Now, as I look at those two, there isn't really a clear connection. 0 degrees Celsius, you're at 15 and 16. We're at 13 degrees, 24 and 23. One's higher, one's lower. So it doesn't seem to be truly impactful if you're storing at 0 or 5 degrees in terms of how many are going to germinate. But it's clear that 0 to 5 degrees is the range that you should have the temperature set for when you're storing them. And if you store them for 10 weeks and then have them germinate at 18 degrees Celsius, that's when you're going to get the most amount of germination. So now you're combining the two experiments together, looking at the data and the trends, trying to come up with clear conclusions about the best way to design the experiment and run the experiment to give you the most amount of seeds, or things to avoid in an experiment where you're going to have the least amount of germination happen. These two data tables come from a chemistry passage. And what happened here was a piece of filter paper with certain solvents were put into certain solutions were put into a solvent. The solutions were made up of these different ions over here. If you don't know what these words mean, it's not a huge deal at this point because, again, we're looking to see trends and information about these ions and about these solvents. And so those key terms are not that important for us to be able to analyze the information. We know we have 5 different ions, whatever those are, and they all give us different data that we're going to be looking at. What happens is, on this piece of filter paper, and it explains this in the passage, you put a spot of the solution and you have a solvent, and over time these two run up the filter paper. and they separate. The distance between the separations, or the ratio of how much they separated, is this RF value. So we'll explain a little bit more about that as we get into the experiment here. But what we have are two different tables, and what we also see is that in table 1 we had these ions that were listed. In table 2 we just have samples with RF factors and colors. So what we can do is compare the different RF factors between these samples that we don't know what they're made of and the RF factors for these samples where we have the ions to figure out maybe what ions are in the samples. We also have the color that was made between the solvent and the solution. So we have the spot colors of these different samples, and we have the spot colors of the known ions. Again, the purpose of that is to be able to say, so sample 2 was most likely made up of these different ions because of the RF values or because of the spot colors. So we're going to be comparing back and forth between the two tables and looking for similarities between them. So questions that are asked in this passage or about this passage and about this data are going to be doing exactly what I was saying here. One question that's in this passage says the information in tables 1 and 2 support the conclusion that sample 3 contains. The answer choices are then looking for which different elements or which different ions make up sample 3. So what we want to take a look at are the different RF values between the two tables and the different spot colors. So I have an RF value in sample 3 of 0.08 and a color of pink. Well, nickel has an RF of 0.08 and pink. So sample 3 probably has some nickel in it. 0.78 in yellow, well, cadmium has 0.78 in yellow. So I would say sample 3 probably also has cadmium in it. So we have nickel and we have cadmium. Then we have 0.95 and brown black. Now as I look at the data table over here, again I have brown black for cobalt and brown black for mercury. However, cobalt's brown black had an RF of 0.35, whereas mercury was 0.95. So the data that matches would support mercury, not cobalt. So the question asks which ions make up sample 3. It would be nickel, cadmium, and mercury, looking for where the data between the two tables is the same. Another question from this passage asks which ion moved the fastest up the table, the filter paper. Well, it explains in the passage that if you didn't know what RF meant, and you'll learn about that in biology and chemistry most likely, and then in forensics again we'll look at this if you take that course as a senior. As you look at this information, the RF factor shows you how fast an ion moved up the paper, how much it's separated from the solvent. The solvent will move at a consistent rate, so the greater the RF value, the further the the solution got from the solvent. So it's very easy to take a look at the RF values and put these in order of speed. Mercury had the highest RF value, 0.95, therefore it went the fastest. And then in this table it happens to go in order, where cadmium would be the next fastest, then copper, then cobalt, and then nickel would be the slowest in the separation. Again, looking at trends within the data, looking at comparisons between the two tables to make conclusions back and forth between knowns and unknowns and making connections to come up with valid conclusions. The last set here we're going to take a look at before you have some practice questions is looking at 4 different substances and how they react, or materials, and how they react to being heated. So what the passage again explains to us here is that you have 1 gram of 4 different materials. That table 1 and figure 1 both relate back to material A, and then table 2 shows material B, C, and D. You should take a look always, for all graphs, all tables, for any time you're looking at them, again at the headings and the axes, to make sure that we're looking at the right spots based off the questions. So as I look at table 1 is looking at time versus the amount of volume of material A, where figure 1 is looking at time, again, in the same time frames from 0 to 24 seconds, making connections, but now we're looking at what's happening to the temperature of A. So if the question asks you for volume, we're going to go right to table 1. If it asks you for temperature, we're going to write to figure 1. Now table 2 is looking at materials B, C, and D, and the boiling point and the amount of heat absorbed as this object is heating. So now if we're asked to consider what's happening to materials B, C, or D, we're going to have to look at table 2 because that's where all the data is for table 2. And if we want to look at the amount of heat being absorbed, then that's where we're going to be looking at also table 2, because table 2 is the only table or the only data representation that has that information in it. What we can see from looking at table 1 and figure 1 together is that as the object was heated, as the temperature increased, it went from being a liquid, an all liquid, into a liquid and gas mixture and stayed at that temperature for a while as liquid was being turned into gas, and then eventually became all gas, and the temperature continued to rise then over time as the gas was heated. So now looking at table 1, as the time went on and we were all liquid, very small volume, then as we converted from liquid over the next period of time here from 2 to 22 seconds, as we were going from a liquid into less and less liquid and more gas, our volume was consistently increasing. And then as we turn into all gas, our volume continued to increase. So from this information, we can tell that the temperature is going to stay consistent during the conversion from liquid into gas. Once the liquid has turned all the way into a gas, then the temperature is going to rise. And when it's all liquid before you have the mixture of two materials, the temperature is also going to rise. We can also tell that the gas takes up more volume than does the liquid. So as the amount of temperature is increasing, the volume is increasing. So a couple of easy connections we can make. Between materials B, C, and D, the only connection that we can make here is that they have a variety of different boiling points. There is a trend there that we could look at. The boiling point is increasing, but the heat absorbed is up and down. So there is no connection necessarily between the heat absorbed and the boiling point. We also can't tell just from the data here how much heat was absorbed necessarily from the tables. So there might be times where we have to also go back and take a look at the material. What we were told is that material A absorbs heat at a rate of 10 calories, which is a unit of heat, per second. So it took from 2 to 22 seconds, or it took 20 seconds to get to boiling. And boiling is where we now have all gas. So during that time where it was boiling and absorbing 10 calories per second for 20 seconds, the heat absorbed would have therefore been 200 calories per second. Another piece of information we can get from the reading of the passage, but most of the information you need for these questions will come directly from the graphs and being able to interpret the graphs and look for trends within the graphs. So the goals here today for understanding tables were to understand the general design of a table, columns and rows, and what's going on inside of the table, what the data looks like and how you can tell what's going on with the table. To understand how to look for trends in data tables. Is there generally an increase? Is there generally a decrease? Where is the highest value, the lowest value? What shows important information from a data table? Understand how to compare a data table from one table to another in terms of the friction lab, for example, where you had the brick versus the wood, and then you had the different masses, and should we be comparing the materials or should we be comparing the masses, and how can we make sure the data that we're looking at is the right data? And then also understanding how to compare and combine data tables and graphs. So with the last example where we had the volume in a table and we had the temperature in a graph, and being able to make connections back and forth between those two tables for the same material. If you have a basic understanding of how to just look at and understand and reason through a table, that will help you with the practice that we have coming up now and also further down the road, both in your science class and on the Science ACT. So hopefully there was value in this for you from that standpoint.